For an elementary calculus-based introduction, see Divergent series on Wikiversity. In mathematics, a divergent series is an infinite series that is not convergent, meaning that the infinite sequence of the partial sums of the series does not have a finite limit. If a series converges, the individual terms of the series must approach zero. Thus any series in which the individual terms do not approach zero diverges. However, convergence is a stronger condition. Not all series whose terms approach zero converge. A counterexample is the harmonic series. The divergence of the harmonic series was proven by the medieval mathematician Nicolas Resme. In specialized mathematical contexts, values can be objectively assigned to certain series whose sequence of partial sums diverges. This is to make meaning of the divergence of the series. A summability method or summation method is a partial function from the set of series to values. For example, Caesar-Roux summation assigns Grandi's divergent series the value 1/2. Caesar-Roux summation is an averaging method, in that it relies on the arithmetic mean of the sequence of partial sums. Other methods involve analytic continuations of related series. In physics, there are a wide variety of summability methods. These are discussed in greater detail in the article on regularization. History. Before the 19th century, divergent series were widely used by Euler and others, but often led to confusing and contradictory results. A major problem was Euler's idea that any divergent series should have a natural sum, without first defining what is meant by the sum of a divergent series. Cauchy eventually gave a rigorous definition of the sum of a series, and for some time after this divergent series were mostly excluded from mathematics. They reappeared in 1886 with Poincaré copyrighter's work on asymptotic series. In 1890 Cicero realized that one could give a rigorous definition of the sum of some divergent series, and defined Cicero's summation. In the years after Cicero's paper, several other mathematicians gave other definitions of the sum of a divergent series. Though these are not always compatible, different definitions can give different answers for the sum of the same divergent series, so when talking about the sum of a divergent series it is necessary to specify which summation method one is using. Theorems or methods for summing divergent series. A summability method M is regular if it agrees with the actual limit on all convergent series. Such a result is called an Abelian theorem for M, from the prototypical Abel's theorem. More interesting and in general more subtle are partial converse results, called Tauberian theorems, from a prototype proved by Alfred Tauber. Here partial converse means that if M sums the series I pound, and some side condition holds, then I pound was convergent in the first place. Without any side condition such a result would say that M only summed convergent series. The operator giving the sum of a convergent series is linear, and it follows from the Harnaud-Banach theorem that it may be extended to a summation method summing any series with bounded partial sums. This fact is not very useful in practice since there are many such extensions, inconsistent with each other, and also since proving such operators exist requires invoking the axiom of choice or its equivalents, such as Zorn's lemma. They are therefore non-constructive. The subject of divergent series, as a domain of mathematical analysis, is primarily concerned with explicit and natural techniques such as Abel summation, Caesar-Roux summation and Borel summation, and their relationships. The advent of Wiener's Tauberian theorem marked an epoch in the subject, introducing unexpected connections to Banach algebra methods and Fourier analysis. Summation of divergent series is also related to extrapolation methods and sequence transformations as numerical techniques. Examples for such techniques are Parder-copyright approximants, Levin-type sequence transformations, and order-dependent mappings related to renormalization techniques for large-order perturbation theory and quantum mechanics. Properties of summation methods. Summation methods usually concentrate on the sequence of partial sums of the series. While this sequence does not converge, we may often find that when we take an average of larger and larger numbers of initial terms of the sequence, the average converges, and we can use this average instead of a limit to evaluate the sum of the series. So in evaluating A equals A0 plus A1 plus A2 plus, we work with the sequence S, where SO equals AO and Sn plus 1 equals Sn plus n plus 1. In the convergent case, the sequence S approaches the limit A. A summation method can be seen as a function from a set of sequences of partial sums to values. If A is any summation method assigning values to a set of sequences, we may mechanically translate this to a series summation method I that assigns the same values to the corresponding series. There are certain properties it is desirable for these methods to possess if they are to arrive at values corresponding to limits and sums, respectively. Regularity. A summation method is regular if, whenever the sequence S converges to X, A, S, equals X. Equivalently, the corresponding series summation method evaluates A equals X. Linearity. A is linear if it is a linear functional on the sequences where it is defined, so that A, Ka plus S, equals Ka, R, plus A, S, for sequences R, S and a real or complex scalar K. Since the terms n plus 1 equals Sn plus 1 or Sn of the series A are linear functionals on the sequence S and vice versa, this is equivalent to I being a linear functional on the terms of the series. Stability. If S is a sequence starting from SO and ZA squared is the sequence obtained by omitting the first value and subtracting it from the rest, so that ZA squared n equals Sn plus 1 ASO, then A, S, is defined if and only if A, ZA squared is defined, and A, S, equals SO plus A, ZA squared. Equivalently, whenever all euro squared n equals n plus 1 for all n, then I A, equals AO plus I or euro squared. Another way of stating this is that the shift rule must be valid for the series that are summable by this method. The third condition is less important, and some significant methods, such as Borel summation, do not possess it. One can also give a weaker alternative to the last condition. Finite reindexability. If A and or euro squared are two series such that there exists a bijection such that I equals or euro squared F, I, for all I, and if there exists some such that I equals or euro squared I for all I, n, then I A, equals I or euro squared. Note that this is a weaker condition than stability, because any summation method that exhibits stability also exhibits finite reindexability, but the converse is not true. A desirable property for two distinct summation methods A and B to share is consistency. A and B are consistent if for every sequence S to which both assign a value, A, S, equals B, S. If two methods are consistent, and one sums more series than the other, the one summing more series is stronger. There are powerful numerical summation methods that are neither regular nor linear, for instance nonlinear sequence transformations like Levin-type sequence transformations and Parther-Copyright approximants, as well as the order-dependent mappings of perturbative series based on renormalization techniques. Taking regularity, linearity and stability as axioms, it is possible to sum many divergent series by elementary algebraic manipulations. This partly explains why many different summation methods give the same answer for certain series. For instance, whenever RA permil 1, the geometric series can be evaluated regardless of convergence. More rigorously, any summation method that possesses these properties and which assigns a finite value to the geometric series must assign this value. However, when R is a real number larger than 1, the partial sums increase without bound, and averaging methods assign a limit of A. Classical summation methods. The two classical summation methods for series, ordinary convergence and absolute convergence, define the sum as a limit of certain partial sums. Strictly speaking, these are not really summation methods for divergent series, as by definition a series is divergent only if these methods do not work, but are included for completeness. Most but not all summation methods for divergent series extend these methods to a larger class of sequences. Absolute convergence absolute convergence defines the sum of a sequence of numbers to be the limit of the net of all partial sums arc1 plus AKN, if it exists. It does not depend on the order of the elements of the sequence, and a classical theorem says that a sequence is absolutely convergent if and only if the sequence of absolute values is convergent in the standard sense. Equals sum of a series equals, Cauchy's classical definition of the sum of a series A0 plus A1 plus, defines the sum to be the limit of the sequence of partial sums A0 plus n. This is the default definition of convergence of a sequence. Now RLUND means, suppose Pn is a sequence of positive terms, starting from Po. Suppose also that if now we transform a sequence S by using P to give weighted means, setting, then the limit of Tn as n goes to infinity is an average called the NaRLUND mean NP, S. The NaRLUND mean is regular, linear, and stable. Moreover, any two NaRLUND means are consistent. Caesar-Roux summation equals, the most significant of the NaRLUND means are the Caesar-Roux sums. Here, if we define the sequence pk by, then the Caesar-Roux sum ck is defined by ck, s, equals n, pk, s. Caesar-Roux sums are NaRLUND means if Ka permel 0 n, and hence are regular, linear, stable, and consistent. CO is ordinary summation, and C1 is ordinary Caesar-Roux summation. Caesar-Roux sums have the property that if H, K, then CH is stronger than CK. Abelian means, suppose I equals I0, I1, I2, is a strictly increasing sequence tending towards infinity, and that I0 a permel 0 n. Suppose converges for all real numbers x greater than 0. Then the Abelian mean I is defined as. More generally, if the series for f only converges for large x but can be analytically continued to all positive real x, then one can still define the sum of the divergent series by the limit above. A series of this type is known as a generalized Dirichlet series. In applications to physics, this is known as the method of heat kernel regularization. Abelian means are regular and linear, but not stable and not always consistent between different choices of I. However, some special cases are very important summation methods. Abel summation equals. If In equals n, then we obtain the method of Abel summation. Here, where z equals exp, ax, then the limit of E, x, as x approaches 0 through positive reals is the limit of the power series for E, z, as z approaches 1 from below through positive reals, and the Abel sum A, s, is defined as. Abel summation is interesting in part because it is consistent with but more powerful than Caesar-Roux summation, A, s, equals ck, s, whenever the latter is defined. The Abel sum is therefore regular, linear, stable, and consistent with Caesar-Roux summation. Lindell paragraph F summation equals, if In equals n log, n, then we have. Then L, S, the Lindell paragraph F sum, is the limit of E, x, as x goes to 0. The Lindell paragraph F sum is a powerful method when applied to power series among other applications, summing power series in the Mittagler star. If G, Z, is analytic in a disk around 0, and hence has a Maclaurin series G, Z, with a positive radius of convergence, then L, G, Z equals G, Z, in the Mittagler star. Moreover, convergence to G, Z, is uniform on compact subsets of the star. Analytic continuation. Several summation methods involve taking the value of an analytic continuation of a function. Analytic continuation of power series equals, if I pund ANXN converges for small complex x and can be analytically continued along some path from x equals 0 to the point x equals 1, then the sum of the series can be defined to be the value at x equals 1. This value may depend on the choice of path. Euler summation equals. Euler summation is essentially an explicit form of analytic continuation. If a power series converges for small complex Z and can be analytically continued to the open disk with diameter from a 1/q plus 1 to 1 and is continuous at 1, then its value it is called the Euler or sum of the series AO+. Euler used it before analytic continuation was defined in general, and gave explicit formulas for the power series of the analytic continuation. The operation of Euler summation can be repeated several times, and this is essentially equivalent to taking an analytic continuation of a power series to the point z equals 1. Equals analytic continuation of Dirichlet series equals. This method defines the sum of a series to be the value of the analytic continuation of the Dirichlet series. At s equals 0, if this exists and is unique. This method is sometimes confused with zeta function regularization. Zeta function regularization equals, if the series for positive values of the AN converges for large real S and can be analytically continued along the real line to S equals a 1, then its value at S equals a 1 is called the zeta regularized sum of the series A1 plus A2 plus. Zeta function regularization is nonlinear. In applications, the numbers I are sometimes the eigenvalues of a self-adjoint operator A with compact resolvent, and F, S, is then the trace of OS. For example, if A has eigenvalues 1, 2, 3, then F, S, is the Riemann zeta function, I paragraph, S, whose value at S equals a 1 is a 1/12, assigning a value to the divergent series is 1 plus 2 plus 3 plus 4 plus A. Other values of S can also be used to assign values for the divergent sums I paragraph, 0, equals 1 plus 1 plus 1 plus, equals minus 1/2, I paragraph, minus 2 closing round bracket equals 1 plus 4 plus 9 plus, equals 0 and in general, where bk is a Bernoulli number. Integral function means, if j, x, equals I pound pn x and is an integral function, then the j sum of the series AO plus is defined to be if this limit exists. There is a variation of this method where the series for j has a finite radius of convergence at and diverges at x equals r. In this case one defines the sum as above, except taking the limit as x tends to r rather than infinity. Borel summation equals, in the special case when j, x, equals x this gives one form of Borel summation. Willeran's method equals, Willeran's method is a generalization of Borel summation to certain more general integral functions. J. Willeran showed that under certain conditions it is equivalent to defining the sum of a series as where h is the second derivative of g and c, n, equals ag, n. Moment methods. Suppose that d1/4 is a measure on the real line such that all the moments are finite. If AO plus A1 plus is a series such that converges for all x in the support of I1/4, then the sum of the series is defined to be the value of the integral. If it is defined Borel summation equals, for example, if d1/4 equals ax dx for positive x and 0 for negative x then I1/4 n equals n. And this gives one version of Borel summation, where the value of a sum is given by. There is a generalization of this depending on a variable I plus or minus, called the sum, where the sum of a series AO plus is defined to be if this integral exists. A further generalization is to replace the sum under the integral by its analytic continuation from small t. Miscellaneous methods. Hausdorff transformations equals, Hardy. Har paragraph LDER summation equals. Hutton's method equals, in 1812 Hutton introduced a method of summing divergent series by starting with the sequence of partial sums, and repeated applying the operation of replacing a sequence SO. S1 by the sequence of averages 2. And then taking the limit Ingham summability equals, the series A1 plus is called Ingham summable to S if Albert Ingham showed that if I is any positive number then summability implies Ingham summability, and Ingham summability implies summability Hardy. Lambert summability equals, the series A1 plus is called Lambert summable to S if a series is summable for any k then it is Lambert summable to the same value, and if a series is Lambert summable then it is Abel summable to the same value Hardy. Leroy summation equals, the series AO plus is called Leroy summable to S if Hardy. Mittelgelaufler summation equals, the series AO plus is called mythical summable to S if Hardy equals Ramanujan summation equals. Ramanujan summation is a method of assigning a value to divergent series used by Ramanujan and based on the Euler-Maclaurin summation formula. The Ramanujan sum of a series f(0) plus f(1) plus depends not only on the values of f at integers, but also on values of the function f at non-integral points, so it is not really a summation method in the sense of this article. Riemann summability equals, the series A1 plus is called summable to S if Hardy. The series A1 plus is called A2 summable to S if Rice means equals. If IN form an increasing sequence of real numbers and then the Rice sum of the series AO plus is defined to be valor copyright e Poussin summability equals, the series A1 plus is called VP summable to S if Hardy. See also, 1 or 1 plus 2 or 6 plus 24 or 120 plus AA a Silvermani Toeplitz theorem. Notes. References, Artica, G.A. Fernandez, F.M. Castro, H. Large-order perturbation theory and summation methods in quantum mechanics, Berlin, Springer Verlag. Baker, J.R., G.A. Graves Morris, P. Part the Copyright Approximants, Cambridge University Press. Brzezinski, C. Zaglia, M. Redovo, Extrapolation Methods. Theory and Practice, North Holland. Hardy, G.H., Divergent Series, Oxford, Clarendon Press. Lugia, J.C. Zinn Justin, J., Large-order behavior of perturbation theory, Amsterdam, North Holland. Volkov, II, Lindell. A paragraph F summation method, in Haswinkel, Michiel, Encyclopedia of Mathematics, Springer, ISBN 978-1-55608-010-4. Zakharov, A.A., Abel summation method, in Haswinkel, Michiel, Encyclopedia of Mathematics, Springer, ISBN 978-1-55608-010-4. Haswinkel, Michiel, ed., Rice summation method, Encyclopedia of Mathematics, Springer, ISBN 978-1-55608-010-4.